So my intention is to present this result with as much the detail as possible. My initial plan was to, have few slides in the end, and then write a lot of stuff on the board. But then, time is still limited. So in the end, I ended up having, more slides than I had planned. But I guess that would be fine. I will still do some, some arguments on the blackboard, definitely. But let's see how it goes, okay? And so I guess we'll have this small break at some point. So, feel free to leave, or all right, let's see how this goes. So, okay, so let me, get straight to the point. Oh, right. Okay, so everybody knows what Aleph-1 Suslin trees are, and of course, interrupt me if there's anything that you don't know, you want to see more detail of. Okay, just let's keep this open. All right, so let me say a few things about what was known about existence of Aleph-2 Suslin trees in various theories in the 70s. So that will be my starting point. So, for example, Jensen proved that the existence of an Aleph-2 Suslin tree follows from either saying you have CH and this particular diamond here on Cov omega 1, but also if you have square omega 1, so this square sequence on omega 2, and this other diamond. And the second result was proved by Gregory when he proved that you have GCH together with a non-reflecting stationary set. This set here, that's something that follows from square. That then you also have an Aleph-2 Suslin tree. So in any case, so you have Suslin trees in many situations. And then around the same time, in the late 70s, Leiber and Schellach proved that if there's a weakly compact cardinal kappa, then there's a forcing extension in which kappa becomes omega 2. CH holds, and therefore you have Aleph-2 Aronszajn trees, and they are all special. So in particular, there are no Aleph-2 Suslin trees, right? And special here means that there's a function from the tree into omega 1 that sends comparable nodes to different colors. Okay, so the proof of the Levy-Schellach result proceeds by, well, you first collapse kappa to become Aleph-2, so you Levy collapse it, and then you run a countable support iteration of length kappa plus, in which you are fed with names for with kappa Aronszajn trees, and then you specialize all of them one by one. So that's all you do. And but you have to show that things go well, and for that you use the weak compactness of kappa in a crucial way, in order to show that the iteration has a kappa chain. In the Leiber-Schellach model, 2 to the Aleph, so you preserve. The iteration is, a sigma close, so you don't add reals, so you preserve CH. But 2 to the Aleph-1 is blown to become Aleph-3, and the following remain the major. So can you have, is ZFC plus GCH consistent with the non-existence of Aleph-2 Suslin trees? Okay, so right. I want not that I need to, but I want to talk just briefly about how we got to do what we did. So to motivate this, I want you to flag these slides on forcing with finite symmetric systems of models as side conditions. Okay, so this was the origin of these things, of the method to prove the main result. Okay, so finite support forcing iterations involving symmetric systems of models, of countable models, think for the moment, as side conditions are useful in situations in which, for example, you want to force consequences of classical forcing axioms like PFA, consequences at the level of H omega 2 to hold together with a continuum large, right? So, PFA implies that the continuous size Aleph-2, but maybe you want to do a conjunction of these two things, and then this method, comes up naturally for this. So, a symmetric system is the following thing. It's so you fix a cardinal kappa, could be anything, and this T as a predicate of H kappa, then you see that the finite collection of countable subsets of H kappa is a T-symmetric system if, well, every n in the collection is an elementary substructure of H kappa with this predicate. So T, think of T as some sort of truth predicate. Then if you have two models of the same height, so the same intersection with omega 1, then there's a unique isomorphism, which I will always denote these isomorphisms by psi and 0 and 1 between the models, and it's the identity on the intersection. Then the collection is closed under these isomorphisms, right? So you have two models of the same height and something in n0, then the image of that is in the collection. And then you have this, this extra requirement, which is not really needed for what I want to discuss next. Okay. So, so this symmetric system is some nice matrix of models. Now, the pure side condition forcing would be simply forced with these symmetric systems under reverse inclusion, okay? Right, and now I want to argue that when you do that, you preserve CH. So you add this matrix of models that will cover the whole of H kappa. So it's some Morassi type object, this big thing, but you preserve CH if you have CH. And the point is that, well, and this exploits the fact that given any two models in a symmetric system of the same height, well, the isomorphism between them is actually an isomorphism when you add this predicate, when you add the symmetric system as a predicate. So the proof is the following. You take omega 2 sequences an omega 2 sequence of names for subset of omega, and suppose that n forces that they are all different. Okay, and I'll get a contradiction. Now, for each xi, you fix some n xi, some sufficiently correct model that contains the condition and the name, and the xi name. Fine. And right, okay. Right. Now, by CH, I confine two indices so that the corresponding models are isomorphic. And also, I can take that there's isomorphism between these two structures, right? When I throw in, a predicate for this name and whatever, and say a satisfaction predicate for this structure here, some predicate using which I can define the forcing. Okay, now I extend, script n by throwing in these two models on top, and that's a symmetric system. But then n star, you consider it's both. it's generic for n xi and for n xi prime. But now I take some extension n prime of this condition I built, and suppose that it forces that n is in R xi. Okay. Then there's an n double prime that extends n prime and some m in n xi, that forces that n is in R xi, and that's by genericity. But that now by symmetry, and this condition, this big condition here, also extends psi of m. But psi of m forces by, since given that it's an isomorphism for a T star, psi of m forces that n is in psi of R xi, which is R xi prime, right? So this is true because, as I said, the forcing is definable using in H kappa with T star as a predicate. All right. Okay. So so n double star extends this condition. So that's it. So we've shown that n star forces that R xi is contained in R xi prime, and the other inclusion is symmetrical, and that's a contradiction, right? Because n was forcing that they're all different. Okay, so this is a warm-up for a part of the proof that we'll see later. But now, yes. You do add reals? Or? You do add reals. You add Aleph 1 many reals, yes. And you add Cohen reals. And only Cohen reals. This is strongly proper. Now, in typical forcing iterations with symmetric systems, side conditions, while the continuum is large in the final extension, as I mentioned, And that's because even if P0 can be seen as a first stage of those iterations, the forcings are designed to add reals at all successive stages. What you may want to try at this point is to extend the following. So extend the symmetry requirements also to the working parts in the hope that you can, this way you can force something interesting to hold together with CH. All right. So that's not what I'm going to talk about, but I'll say that, well, while visiting Mohammad Golshani in Tehran last year, we thought about implementing these ideas with, well, I mean, not with a continuum, but one level up, with, preserving 2 to the Aleph 1 being Aleph 2, and with Aleph 1 sized models. Okay, I mean, it's the same thing. Instead of countable models, right? And to implement these ideas in the context of the Lever-Shelach construction, in order to address that problem, right? In order to build a model of GCH with no Aleph 2 Susan trees, and we eventually succeeded. Okay, so the theorem is that I want to present the proof of is this one. So kappa is weakly compact. Then there's a generic extension in which GCH holds. Kappa is Aleph 2, and all Aleph 2 Aronszajn trees are special, and therefore there are no Aleph 2 Susan trees. Okay, so that's the goal. Now, okay, so here's how I start the proof. Kappa is weakly compact, and well, to start with, I can assume that I have, GCH from kappa onwards, because I can force that while not adding subsets of kappa. And now I also fix this bookkeeping phi, so function from kappa plus to h kappa plus, so that everything is in kappa plus is enumerated by phi unboundedly often. So phi exists because I have this arithmetic. And I also fix this sequence phi alpha, alpha less than kappa plus, this sequence of predicates, truth predicates for h kappa plus, which will be increasingly expressive. So the first one is just phi, the bookkeeping function. And then for non-zero alphas, phi alpha just codes the satisfaction predicate for this structure, where you have the sequence of all previous predicates and phi. Okay.
So sorry. So phi is just gonna list all the future names
yes.
for Susan trees.
Yes.
Right, and then so that's standard, but
yes.
we don't usually see the second part. Right?
Well, no, but it's convenient because it's really important.
Yeah.
Sure. Yeah. I mean, I'll have to refer to these predicates when I'll see in a moment.
The satisfaction, you mean the forcing relation, or?
No, just the satisfaction, the first order satisfaction predicate. Okay.
And alpha go there and plus.
Alpha less than kappa plus, yes. Yeah. All right, so let script f be the weak compactness filter on kappa. So it's good that I fixed this right from the start. So, which is a filter on kappa generated by the sets of this form. So, okay, you fix a pi11 sentence psi that holds in B kappa, with some parameter B is some subset of B kappa. And then look at all the set of all lambda such that the psi reflects to V lambda. Okay, so F is a proper normal filter on kappa. That's equivalent to kappa being weakly compact. And let also as script S be the collection of all F positive subsets of kappa, right? So all X intersect all measure 1 sets. All right. Now, here's the main ingredient of the proof. Okay, so this is the main idea. It's revisionism, which is so. What is revisionism? It's changing history, right? So, in the light of what we know or believe now, we change history. So, copying information from the future into the past. All right, so we call, I'll call a pair like this, n0, gamma 0, and 1 gamma, an edge below, an edge just for lack of a better name. It's two things. is an edge below beta if the following happens. So for both of these things are models of H kappa plus of well, okay, so their intersection with kappa is an ordinal. Okay, so that's the height of the model. It's small, it has size less than kappa, it has the same size as its height, and it's closed on the sequence of size less than the size. Okay. Right. So typically, you know, this, yeah. Okay. And also, gamma I is an ordinal which is in the closure of this of ni intersection. Well, psi plus 1, psi less than beta. So it goes only up to beta at most. Okay. It's in the convenience of this thing in the order topology. And Ni is elementary sub model of H kappa plus with phi alpha for every alpha below the marker, right? So this gamma I tells us up to which point Ni is relevant as a model. Okay, so you have this here. Now these two models are isomorphic by and this is the isomorphism. Right, I mean they have the same height, I mean in particular they have the same height, but they are isomorphic, and the isomorphism respects the predicates. So n0 phi alpha is isomorphic to ny phi of the image of alpha whenever alpha is less than the marker and the image is sent to something less than the marker of the other model, right? So whenever this makes sense. Also, you require that the isomorphism is the identity on the intersection, and that it doesn't, and it goes to something, and that the psi the image of psi is less than or equal than psi for every psi in n0, right? So n1 is sort of a projection of n0, okay? It's, so you have this model n0, and n1 is something like this. Okay. Yeah. No, it doesn't have to. It doesn't have to, but the model is. I mean, it's not gamma. There's no relation between gamma 0 and gamma 1.
Is there any relation with beta and delta? So there's 4 ordinals here.
Mm-hmm. No, so this beta is fixed, right?
Sure.
Yeah.
But gamma 0 and gamma 1 then could be bigger or smaller.
Gamma 0, gamma 1 are not bigger than beta.
Oh, okay. Yeah.
Right. Mm-hmm. So they are markers that they can only be as much as beta, so but they could be anything. And all I'm saying is that, right, and the isomorphism has to respect things that are sent, you know, things, as I said, so an alpha less than gamma 0 that is sent to, that happens to be sent to something below gamma 1, then I have this agreement. Okay. Mm-hmm.
So where does the asymmetry come from?
The asymmetry?
You said that n1 is somehow a projection of n0, but
yes,
not
because you have this.
Because it goes up.
Because it goes down.
Oh,
it goes down.
Oh, I see. Okay.
Right? I mean, that's why it's asymmetric. Okay. Right? And then the markers, so this could be gamma 0 and gamma 1 could be this one, right? Okay. So this will be the main ingredient. Now, given stage beta, we build Q as a forcing with side conditions that consists of sets of edges below beta. Okay, and there'll be no structure whatsoever, you know, between the edges. So it's some, you know, it's some arbitrary. And now, given an edge like this, in the side condition, the thing is we will copy information that's sitting in n0 attached to some ordinal alpha less than gamma 0 via the psi, the isomorphism into n1 if psi of alpha happens to be less than gamma 1, right? So that's what we will have to do. We will promise information, we will copy information from n0 into n1, not necessarily the other way around. So we do not require that information in n1 attached to this ordinal be copied into n0. Okay. Now, given models with markers, okay, this is a piece of notation, and gamma, okay, I have 3 models with markers here, like this, and I have, you know, this will be, you can see this will be an edge, right? Anyway, these are isomorphic models, and then n gamma is in n0. Then I just denote this thing that it's syntactically meaningful because it depends on gamma, n0, gamma 0, Okay, so that's simply the supremum of the set of ordinals psi plus 1, which are n1, so that that tells us, it tells me the least ordinal to which I should send gamma, okay, by this copying procedure. That's what it's saying, right? So it's a supremum of the set of ordinals of, in this model, such that psi is in, let's say, is less than the image of the marker of n, okay, that makes sense. The pre-image of it is less than gamma 0, and psi is less than gamma 1, right? So that's like the supremum of the ordinals to which, it's the least ordinal to which I should morally send gamma. I should, to which, let's say, not, such that the image of n in n1 should have its marker. That's what I mean. Okay? Does it make sense? Okay. Right. Now, assuming that I have alpha less than kappa plus, and the Q alpha has been defined, and this forcing satisfies CH and kappa is all of 2, so in particular I have all of kappa Aronszajn trees, then I just fix T alpha in H kappa plus be a canonically chosen Q alpha name for a kappa Aronszajn tree, which happens to be phi alpha if phi alpha happens to be a kappa alpha name for a kappa Aronszajn tree, right? The usual thing. So this is my sequence of names given by the bookkeeping. And I will assume for each row less than kappa that the row level of the tree of T alpha is, you know, is this, okay, is all pairs row comma nu, where nu is an ordinal omega 1.
This is the original phi 0.
Say it again?
The phi of alpha, the phi is the phi 0, the first
yeah.
one. Yeah, because then you wrote phi sub alpha, but you mean phi of alpha.
Phi sub, oh, right, that should be, yeah, sorry, yeah, that's phi of alpha, sure, yes. Yeah. So, and here's the definition of the forcing, okay. I mean, okay, it's not all on this slide, sorry. But okay, here's how it starts. So let beta less or equal than kappa plus, and suppose that Q alpha has been defined for all alpha less than beta, okay? Now, a condition in Q beta is an ordered pair of the form, okay, of this form. So you have this working part, FQ, and you have the side condition tau Q with the following properties. Okay, so with the following properties. So FQ is a countable function whose domain is contained in Q kappa intersection beta. So I only have stages below beta, and it's countable, so it's countable support. And such that the following holds for every alpha in the domain. If alpha is 0, then FQ of alpha is simply a condition that the Lebesgue collapse, you know, turning kappa into omega 2. And if alpha is positive, is greater than 0, then FQ of alpha is a countable function from kappa cross omega 1 into omega 1, right? So which will be forced to be a specializing function, of course. And now tau Q is a countable set of edges. Oh, hi. It's a countable set of edges below beta. Okay, so that will be the side condition. I think that was... Okay, so these are the first 2 clauses. Okay, I'm starting to define this the main forcing that will prove the theorem. Okay. Okay. Right. So I've okay. So I just start with some, you know, some notation, and then, well, you know, I mean, ask me at some point what? So, and now I'm building this iteration of length kappa plus, and I say, well, suppose I have a stage beta, and I defined Q alpha for all lower, for previous alphas, and then the condition is just, well, it has these two parts. It has this working part that is this countable function, so it's with countable support, where the first at the first stage I take a condition in the Levy in this Levy collapse, turning kappa into omega 2, and then at all other stages I look at the countable function from kappa cross omega 1 into omega 1, which will be forced to be some specializing function for a tree, and tau cap q is a countable set of edges which I just defined before. Anyway, so then I have this copying requirement here, right? That I have, okay, so suppose I have an edge in my side condition, then I have to do, two things. So if I have another edge, n0 prime, gamma 0 prime, and in n0, which is, okay, in n0, then I have to, well, I have to take the, I have to look at the copy, I have to take the copy of that edge in some meaningful way, right? So then this other edge has to be in the side condition where, well, the model is just the image of n0 prime by the isomorphism. The marker is something which is at least that ordinal that I had defined, right? And similarly for the other one, okay? And then for the working parts...
Are you confused with notation? So the edges, I mean, you're taking points which are in this name for this tree, for this kappa tree. An edge is meaning something that's connected in the tree order.
No.
Oh no, what is it? What is it?
Oh, no. So edges, so yeah, let me just show you. An edge is, okay, hang on a second. What was this? Oh, yeah, this one. So that's the, okay, so this is the main ingredient. So I will, yeah, so I'll have pairs of models with markers where, okay, so this is some close enough model of size less than kappa.
Oh, it's a model.
Yeah, yes, and then gamma 0 is an ordinal that tells us up to which stage is n1, relevant as a model and active. And then I say that the models are isomorphic via an isomorphism that respects the predicates whenever it makes sense, and which is the identity on the intersection, and it's regressive. The psi of psi is less than or equal to psi for every psi in n0.
So is this, roughly speaking, a Lever-Shallot iteration where you specialize, but with side conditions that make
it? Yeah, and these are the side conditions, yeah. And now, and this was the picture. So you have n0, and then n1 is something, maybe. Right? It's a sort of a projection. Okay, so that was, yeah. Okay. Now going back to, okay, so this was the copying, right. So we were in this condition 3. Okay, so this here. And then, so that was for the side condition, and for the working part, well, what you would expect. So you take an alpha in the domain of f, which is in n0, and it's below gamma 0, psi of alpha is less than gamma 1. Then, okay, then psi of alpha is also in the domain of f, and f of alpha, restricted to the height of n0 cross omega 1 is contained, which is, of course, is psi of this thing, right? Because it's identity. It's contained in f q of, at the fq of the image of alpha. Okay, so I mean that's exactly what it means to copy the information that sits on alpha on psi of alpha. Because the again, the
FQ is partial specializing information.
Yes, exactly. Yeah. Okay, so simply because psi is the identity on this on this set here. Now, for all alpha less than beta, I have to say, what you would expect in an iteration, namely the natural restriction of Q to alpha is a condition in Q alpha. And that's a natural thing. So you just restrict the working part to alpha, and then this thing, right? I think I haven't defined this, and the side condition also to alpha. And what that means is simply that I just drop the markers to anything to the highest meaningful thing less or equal than alpha. Okay, so tau q of alpha would be simply n0, and then I guess is okay, so let me just say a second what this means. So that's for whenever I have okay, and this notation means, well, look at the highest ordinal in the closure of n0 intersection, you know, the ordinals, which is less or equal than this thing.
But your side conditions are countable, isn't that?
No, well, I mean, the set of edges is countable, the models are not. The models have size less than kappa. Mm-hmm. But yes, I mean, the side condition itself, so the set of edges, the set is countable, yes. So everything is countable. Okay, now, okay, and then this is the last clause here. Okay, sorry about this. So I promise, I mean, this is the last clause, only five. So, right, and that's for technical reasons that come up in the proof of the kappa chain condition. So, okay, the following holds for every non-zero alpha less than beta. Oh, okay, the first thing is sort of what the natural thing you would expect. I haven't still mentioned. So if alpha is in the domain of f, then q restricted to alpha forces, of course, that f q of alpha is a partial specializing function for T alpha, of course. Now, but then also, if I have an edge in the condition in tau q, and right, and alpha is in n0, it's below the marker, then I require that q alpha plus 1 intersection n0, so all conditions in q alpha plus 1 that are in n0 be a complete suborder of this other thing, something that I'm going to define now. Okay, which is some suborder of what morally should be q alpha plus 1. Of course, if when beta is equal to alpha plus 1, this definition, if I just put q alpha plus 1, this will be completely circular. So that's why I need to define some, you know, I need to define an approximation at this point to the intended forcing. Okay, otherwise this doesn't make sense. So, so what this amounts to is that the definition of the forcing is some recursive definition on the height of the models, you know, strictly speaking. So, okay, so q n0 alpha plus 1, and I'll draw a picture in a moment, is simply the partial order whose conditions are, well, ordered pairs, again, like what I have, so fp tau p, such that, well, again, fp is a function of domain, with domain containing alpha plus 1. If alpha is there, then fp of alpha is a countable function of this form. Tau p is a set of edges below alpha plus 1. Now, the markers of these edges, so are at most alpha whenever whenever I have an edge which is not in n0. So, okay, so only things in n0 can have the marker alpha plus 1 and therefore be in the forcing which I have already defined. So this makes syntactical sense. Now, p restricted to alpha is in q alpha, fine. P restricted to n0, and this means the natural thing. So you restrict tau, you know, the tau thing to n0, and then for the function you restrict the domain to n0, and then take the intersection. Okay, the natural thing. This restriction is in q alpha plus 1. So again, that makes sense. And if alpha is in the domain of fp, then p restricted to alpha forces that this is a partial specializing function for this tree. Again, this makes sense. So, you know, I mean, this, again, so this forcing is what q alpha plus 1 should be, except that all the markers that of edges that don't come from n0 simply are alpha at most. So it makes sense. And the extension relation is just a natural one. So okay.
Tell me again what in condition 6 p restricted to 0 is in q alpha plus 1 means what exactly?
Well, I mean it.
Q alpha plus 1 yet?
Well, I'm defining q alpha plus 1 by recursion on the on the suprema of the heights of the models,
So
right?
this is already defined.
So that's already defined.
I see. Yes. I see. So I have
Right.
a sequence of q alpha plus 1s.
Yeah, you know. Right. So I'm fixing this edge, right, in this tau q, which I'm defining what it means for q to be in q alpha plus 1. That's when beta is alpha plus 1. Sure. Right. So that has already been defined. Right. So. Okay. And fine. But you know, I mean, if you want to keep in the back of your mind, so why am I doing this? Because I would like to.
You're worried about the kappa-cc? Is that what you're worried about?
Yeah, I mean that will come up, but it's kind of technical. I cannot say yet why it's in it. But no, but I mean, no, I mean it's hidden somewhere in something we'll see, hopefully. But yes, we need something like this. Now, of course, I mean, what we really would like, or I mean, we would be happy if we had that. You know, whenever you have an edge and an alpha, then okay, then this is an elementary complete suborder of this one when you just drop the sub-index. But of course, I cannot express that. I mean, let's say that would be enough for the I mean, that would be. I mean, this is enough for the application, but that would be like the natural thing to expect. Yeah.
Just talked about the first coordinate and the second coordinate.
Yes, and I guess.
Any relationship between the edges?
Between the?
The edges when you have
between the edges. No, I mean this refers to the. I mean this also you know involves edges coming. You know the restriction. Yes, that's fine.
And you need to get the q alpha plus. So you have this complete. You have the complete suborder. You know the interchange state maximal.
Yes.
So you're forbidden to put things into
any condition here will be compatible with any maximal anti-chain from here.
Yes. And you're saying the existing q alpha plus 1 or the unique q alpha plus 1 which has this property?
So q alpha plus 1 has already been defined. I'm defining q alpha plus 1. Right? I mean, I'm defining q alpha plus 1 by you know recursion on the heights of these ends coming from the edges, if there are any, right? So that's already been defined. So this is already, you know, this is some forcing. This is the forcing I'm defining.
And you say this is obvious that this is a complete forcing, or this will be true?
This is a requirement. So I can only put that edge if this happens to be a complete suborder.
Oh, I see.
It's part of the definition. Yes.
Okay.
So this may not be true. Then in that case, that wouldn't be a legal condition. It's a requirement. It's part of the definition.
Sorry, maybe I misspoke. So globally, this forcing is omega closed?
Yes, it's sigma closed, yeah.
Okay. But it's not kappa-cc, is it?
It's kappa-cc. That's what I mean. That will be the that's the main part of the proof.
Wait, kappa plus cc is just a simple delta system.
Kappa plus is should be easy, yeah, sure. I mean, yeah, sure. I mean, kappa plus cc is easy. So you just have, I mean, the functions are all small, you know, are on kappa.
The forcing only has size kappa plus.
Yes, kappa plus, yeah.
The main thing is the kappa-cc.
Yeah.
Ah, yes, right, the omega-2cc.
Yeah. Yes.
But like maybe Shalai, you first turn kappa into omega-2 at the very beginning. And then you do this.
Right, so, right, exactly. So you, yeah. Yes, okay. And the extension relation for the forcing is the natural one, right? So you extend the supports, you extend the functions on the supports, and then if you have an edge, then you have markers. Get an edge here. Okay.
You add edges, no?
You could add edges,
It
sure.
doesn't
I'm
say
saying
that.
if you have an edge,
You didn't say you added edges.
uh,
edges.
no, yeah, I mean, this comes from here.
Oh, I
think,
see.
Yeah,
For
yes.
every old guy, there is.
Mhm.
Okay.
Yeah, you could have new edges, sure.
Right.
So
Mhm.
if Q is in Q beta
Mhm.
and P is in Q alpha,
Mhm.
stronger than the restriction of Q,
Mhm.
then you can put them together.
Yes.
In the natural way.
Yeah, that will be one of the facts. That will come, but yes, yeah. And that is very nice because, and that's what, okay, I'll say it in a moment. That's fact 3 here. Right. So okay. So the main facts, some of them are easy. Start with we have fact 0, which is that for every alpha beta less than kappa plus, Q beta is definable over the structure when you have the phi beta plus 1, the predicate, without parameters. Okay, just look at the definition. And then the definition, it can be taken to be uniform in beta. Okay, it's the same formula. Okay. You know, if you want me to go back to the definition, just tell me anytime. Then Q1 is essentially the Levy collapse of kappa to omega 2, so it poses this thing. And also, whenever you have a beta, well, Q alpha is a suborder of Q beta for all alpha less than beta. And if the cofinality of beta is at least kappa, then Q beta is actually the union of the previous Q alphas. Okay, and now, also thanks to the fact that you're copying only information from the future into the past, this is a forcing iteration in the sense that a Q alpha is a complete suborder of Q beta whenever alpha is less than beta, right? So you have, as that's what Martin was saying, you have a Q in Q beta and R and Q alpha, which extends the restriction of Q to alpha. Then you can just amalgamate everything in the natural way. You look at FR union the tail of FQ from alpha onwards. You take the union of tau Q and tau R, and that will be a condition. And that's because, yeah, as I said, I mean, just look at the definition. It's look at the geometry of the forcing. Okay, we only require to copy things from the future into the past. So,
So you say that in limit stage kappa you take effect union, but and in limit stages of cofinality omega 1 you don't take direct union?
No, but I mean the models are size less than kappa. The models are not size out of 1. They come from V, right?
They are size less than kappa, which becomes less than omega 2.
Well, that's after the first forcing.
After the first forcing,
yes.
They become of size omega 1.
Sure. Yes. But I'm talking, this is the ground model, right? Yes. I'm talking in the ground model. Yes. So the models come from V, and they have size less than kappa. They're not of size out of 1 in V. Yes. Okay. Right. So also Q beta is sigma closed. Okay, for every beta, and that's very easy. And in fact, well, take any decreasing sequence, Fn of length omega sequence of conditions, then it has a greatest lower bound Q star, where you take, well, just the union of the side conditions, and F, where the domain of F is the union of the domains, and and F of alpha is simply the union of the FQM of alpha for all indices, at least n. Okay, so just the natural thing. And again, this is trivial. Just look at the definition. Just go back to the definition. Look at it. Ah, yes, it's. So in particular, forcing with Q beta doesn't add omega sequence of ordinals. Therefore, you preserve omega 1 and CH. Now, in many arguments I'll do from now on, you will try to run some construction in omega stages, right? Then, I mean, this is very useful because you know that at the limit stage you have this greatest lower bound that will be closed under whichever operation you close the construction under. So you will have, right? So this is very convenient. Also Q, right, I mean, okay, so then Q, this forcing has a kappa-cc, and this is the main, bulk of the proof, which is what I will spend most of the time with. And then it adds, so I'm not doing this yet. Also, it adds kappa many subsets of omega 1, but not more than that. So in particular, it preserves the 2 to the aleph 1 is aleph 2. Now, I'll do this proof now in a moment. It's because it's, okay, it's essentially like the same argument I saw at the beginning, but there's a little twist. And then, well, okay, let me mention that it forces that all aleph 2 Aronszajn trees are special. Okay, let me just say in words why that is true. Well, you have CH, and you do have, so therefore you do have aleph 2 Aronszajn trees. Now, and then you have the kappa-cc, so all of them, you can come, the usual argument, you can assume that they all have names in H kappa plus, which are picked by the bookkeeping function, so eventually you pick them. Now, so eventually you are at some stage alpha where the alpha, you're attempting to specialize the alpha's Aronszajn tree. And now by the, the way you define the forcing, okay, by this thing, that you're adding a partial specializing function for that tree. Now then the conditions, everything in the condition is countable, and you can specialize in omega 1 colors. So you can, given a condition, and any node, you can pick a color which has not been mentioned yet, and also in any FQ alpha prime, because you have to copy it. And then you can just send that node to that color and just close on the isomorphisms. And that's very simple.
Okay, so that want to work on a dense set where the conditions are kind of have check names.
No, the conditions come from the ground model. I mean,
in the iteration you have names.
Yes, but you can.
It's going to be dense to the side.
Yeah, exactly.
That dense set.
Yeah, exactly.
Because you just started talking about what colors have been used.
Yes.
You want to be able to force that and know that.
Yeah.
When defining the partial order, he only includes ground model functions.
Yeah, I mean, right. I mean, I only put ground model functions, but
then it's the standard iteration. Then you have to prove that that's the same as.
Yeah, but the thing is but then you have what you said. I mean, anything.
Yeah. You said it's omega close.
It's omega close, yeah.
No, it needs support because you only have a name for the tree, for the color using the ground model.
Okay, so all right, so that.
So you did the coloring of this function from omega 1 to omega 1.
Omega 1 cross.
Yeah, and so the only thing that you're expecting is the actual tree ordering here on this side.
Yeah, so the underlying set of the tree is also in the ground model.
Okay, so let me just let me sketch the proof of 6, and then we will have the break, and then you can leave, and then we'll have the kappa-cc. Okay. All right, so here's the proof of 6. That Q kappa plus adds less than kappa plus many new subs of omega 1.
I mean, this is what labor Shalat couldn't get, right?
Yeah.
They got everything else.
Yes. Yeah. I mean, this is and this is easy for us. This is easy. So now, of course, now the kappa-cc in their case, well, it was not that trivial either. No, but then, but in our case, it's substantially more complicated.
Right. They could get it, but they were, on the other hand, they weren't doing it.
Yes. Anyway, but this is the easy part for us. Okay. Suppose towards a contradiction and this is like essentially the same mantra that we had before, right? That Q is a condition, and there's this sequence, a kappa plus sequence of names for subsets of omega 1, and Q forces that they're all different. Now, by kappa-cc, I can assume, which I've already, presumably I've already proved, I can assume for each I, that Ri is in H kappa plus, and Ri is a Q beta I name for some beta I less than kappa plus. And now, now let theta.
Sorry, that would only use the kappa plus CC? That would include that?
Yeah, that would just, yeah, sure, that would, sure, yeah, that would be kappa plus CC. So actually, yes. Now let theta be large enough, and for each I, I will find an nx star. Okay, so, you know, elementary submodel of h theta that has the same size as its height. It's closed on the sequence of length less than its size. It contains all the relevant objects, so that's the sequence of the predicates, the iteration, the stage beta I, the name Ri, and the condition Q. And Q alpha intersection n I star is an elementary submodel of Q alpha for every alpha in the model. Okay, now
you need to work.
I'll say how I find this. So this is how I will get the ni. I mean, I haven't justified yet. That's the justification. Okay, so I want to.
I just thought it would follow from the previous things. It doesn't necessarily follow from it.
Well, I mean, you need a bit of argument. You need to use the weak compactness.
Oh, okay.
Yeah.
Maybe,
Yeah. I mean, the last thing is, I mean, you have to work a bit for. You have to work a bit for that. So right. So that's what I want to find. How do I find that? Okay, so it can be found by a pi1 reflection argument using the weak compactness of kappa and the kappa-cc of all Q alpha. Okay, so right, so I take this M star elementary submodel that contains again all those objects. It has size kappa. It's closed under less than kappa sequences. Now, by the kappa-cc of all Q alphas, okay. This Q alpha will be an elementary, right? That's the sorry, that's the other way around. So Q alpha star, which is intersection of Q alpha with M star, is an elementary is a countable suborder of Q alpha for each alpha in M star.
You said it backwards.
Yeah, that's a typo. I mean, that should be here. That's
I see.
Sorry about the typo. Okay, that's a small forcing. Simply because all, you know, I can, because I have a, you know, I have this, I can code all, you know, all, because all maximal anti-chains have size less than kappa. So it's, okay, so now, so right, so I just need to work with this suborder with Q alpha star, which has size kappa, okay. Now, so what I take is...
You say the chain condition is pi 1, 1. You say that all the
Yeah.
internet chains.
Yes.
This is how you're using reflection.
I'll use reflection to get. I mean, for this I don't need.
Reflection?
So for this I just need the kappa chain condition for this one.
Oh, okay.
Right, and now to get smaller, you know, suborders with complete suborders, I need to use the weak compactness, right? So what I say is, well, now let B subset of V kappa code the sequence of the Q alpha stars. Okay. And the sequence of maximal anti-chains of Q alpha stars, right? Okay, so I want to say this is the collection of all maximal anti-chains of, you know. Okay, so now, okay, so I can code these things by a subset of V kappa, and now I take all the maximal anti-chains that are in yes, which is all of them, because M star is closed under less than kappa sequences. Right? Okay, but now you have you can find a suitable pi1 sentence psi with B as the parameter, which expresses, well, you know, the fact that this is the collection of all maximal anti-chains of these forcings and this forcing, and then using that I may find a set C of, you know, measure 1 set C of ordinals delta such that the sentence reflects to V delta. And with the sensible choice of psi, which is what I was mumbling now, it follows that, okay, because of, I can find the delta in C, so that when I take the column closure of delta in M star, that will be close enough and will be, so it will be like this and will be close enough. Of course, it will have this, and it will be such that this happens. So that means I have to psi to say something like, okay, so this is the collection of maximal anti-chains. So this is the sequence, this beta bar sequence of forcings, and this is the sequence of respectively the maximum collections of all the maximal n-tate chains of these forcings.
So sorry. So the ni star needs to have size less than kappa. That's why force.
Yes.
Yeah.
Okay. So that's it. And now, so that's what I argued.
By the way, that filter was the weak compatibility.
Yes. Yeah. Exactly. And now I just denote ni start section h kappa plus for each I. Okay. So I fix these ni's now, and I look at the satisfaction predicate called P for this structure, where I'm coding everything relevant, okay? And now I take another elementary submodel M of H theta that contains all of these objects, has size kappa, is closed under less than kappa sequences. Okay, and now I take some index I0 which is not in M. Okay, but now by a standard reflection argument using the closure of M, I can find a copy in M of these ni0 sitting outside. So I can find some I1 in M for which there is an isomorphism psi between these two structures, right? Okay, and such that the isomorphism is regressive. So psi of xi is less or equal than psi for every ordinal in ni0. Indeed, the existence of such an I1 will follow from the correctness of M in the H theta about the suitable statement which has the sequence of ni's as parameters, a sequence of ni's, q, p, all these things, and the intersection with M of ni0, which is in M because M is closed under less than kappa sequences, right?
Why do you need this M model instead of just a delta system argument?
That's a delta system argument. Right. Well, yeah. I mean, I want to show that ni1 is this projection. Okay, but I guess yes, there are various ways to do it. That's a delta system argument. Yeah. Anyway, so I found this ni1, which is this nice projection of ni0, and I have this isomorphism. And now the rest of the argument you've already seen. So. Okay, I mean not yet. Now I take Q bar will be my extension that is just, so I extend Q by simply putting this node on top. So, okay, right. And now, now I have, okay, now if you look at the definition of Q ni0 alpha plus 1, that was, I mean, that was clearly a suborder of Q alpha plus 1. So therefore, but now I have this condition 4 here, okay? So I have something, so this, I have that I can put also n0 here, and it will be true, okay? So that means that Q, okay, that means that I have this, that Q alpha plus 1 section ni0 is a complete suborder of this funny forcing that I defined for every alpha. So it follows that Q bar is a legal condition. It's a condition thanks to the choice of this ni1 being a projection of ni0. And now I show that this extension shows that these two names are the same. So why is that? Well, suppose not, and then you get the contradiction. So suppose you find some nu and a Q prime extending this one that forces that this happens. And so suppose that it forces that nu is in Ri0 and not in Ri1. Okay. Okay. So now by correctness of that model, you have that there you have a maximal n-tate chain A of conditions in this forcing that decide this statement. The statement nu is in Ri0. Now I have that this has size less than kappa by the kappa-cc. And also I have that, well, the intersection of the model with kappa is an order in kappa, so therefore A is a subset of ni0, right? So, so I can find a common extension of, Q double prime of Q prime, and some condition R in A, which is in the model, and forces that nu is in Ri0. Okay, but now psi was an isomorphism between these two structures here. And by the choice of P, I have, as you know, the same argument as we already seen, the psi of R forces in Q beta I1 that nu is in psi of Ri0, which is Ri1. But then clause 3 in the definition of condition requires me to requires Q double plus to extend psi R. Okay, so that's why that's why it was important that Ni1 was this this projection of Ni0. Okay, so then we obtained that Q double prime force that nu is in Ri1, and that's impossible because it was Q prime was forcing that nu was not in Ri1. Okay, so that's a contradiction, and I think it's a safe place here to stop for now. Yeah.
So the iteration is like kappa plus, but it has only kappa many subsets. So at some point it stops.
Yes.
And in fact, you know this point is the ground model because of kappa-cc.
Yep.
So it doesn't depend on the generic. And you're not claiming this is step 1.
No, no.
Like,
it's not.
It's some magical ordinal where afterwards all the forcing is decided in all the
yes.
You've got all the isomorphism types that are mentioned here.
Yeah, that's how you will. Yeah, I mean that. That would be a bound for something like that. Yeah, it's some ugly ordinal. Yeah.
You can actually exercise it somehow, given explicit upper bound by just saying when have we covered everything.
Something like that. Yeah.
I mean, I guess it's not connected with Kruger and Mota, right? They had this thing. Shooting a club through all of two with finite conditions,
right?
Keeping CH. Well, actually, maybe you and Mota earlier.
Yeah.
You have a whole chain of papers, don't you?
It's all connected. Yeah.
Yeah, keep CH. Similarly with these side conditions.
Yeah.
So this has a history.
Yeah, exactly. I mean, that's what it comes from. Yeah. Okay, so I guess let's have a break.